Hey everybody, I want to talk to you about how to actually calculate p-values in this video. That's going to be the basic idea of what we're going to do. I'm going to do that in the context of doing a whole hypothesis test, and so it gets a little bit long. The actual calculation of p-values is actually is pretty simple. It's really just using your calculator to find the area in a normal distribution, or as we will see, in a t-distribution, which turns out to be pretty common. Which is very easy. I don't recall if we've actually done that. But in the same way that your calculator has normal CDF, it's also got TCDF. It's pretty easy to use. So let me go ahead and go to the notes here and see how we're going to do this. So quick note on t-distributions. So whenever we know S but not sigma, so in other words, if we don't actually have the population standard deviation for our hypothesis test, we're going to have to use a t-distribution. And if you recall from previous videos, most of the time we don't. So for instance, this one here about FDA is responsible for accurate labeling of food packages, et cetera, et cetera. At no point did we say Allison knows that the actual population standard deviation of filled chip bags of this size is, 0.2 ounces. She would have to use a t-distribution because she doesn't know what the population standard deviation would be for that, right? And why would she? I mean, she's an FDA inspector, maybe she would, but you have to have extraordinary extra information to use a normal distribution instead of a t-distribution. Most of the time, you don't actually know what sigma is, and so you end up using a t-distribution most of the time. So here's the idea with a t-distribution. So a t-distribution, let's go ahead and just draw a picture here. So t-distributions are meant to model the standard normal distribution. And so here's some t-distribution. T-distribution is all possible t-statistics, all possible t-scores, I should say, of from a particular population, right? So in the same way that your normal distributions from the central limit theorem are often like, so let's say this is T28. Right? So again, number of degrees of freedom is 28 here. So this is a sample size of 29 in this case. All t-distributions are centered at 0. And then everything on the x-axis, I keep pointing at my screen, everything on the x-axis here is a t-score for some particular sample. Right, that's what's on here. So all the things down there are t-scores. So what that means is we have to calculate the t-score for our sample to get it on this distribution, right? Because that's all this distribution is, it's a bunch of t-scores. So a t-score is basically the same thing as a z-score, it's just to use S instead of sigma. All right, so if you recall, this is how we calculated z-scores. We would do x bar minus mu, so the difference between our sample mean and our population mean, divided by the standard error, right? Which for us before, when we were doing z-scores, was sigma over root n, but in a t-scores, that's over root n. This is the number of standard errors away from the mean that our sample is. That's the way we want to think of this. So here's my quickie example. Let's say you're testing to see if wombats weigh an average of 60 pounds. If you want to model the sampling distribution of x bar for wombats, take a sample of 18 wombats, we got to use a t-distribution with 17 degrees of freedom. Sample size of 18, 17 degrees of freedom. Notice that we don't have any idea about what standard deviation of wombat weight is, right? And so all we can look at then is the standard deviation in our sample, which is S, which is why we're using a t-distribution here. So here's our sample. We get 62.3 pounds with a standard deviation of 5.7 pounds, gives us a t-score of this, right? I plug all those things in. Here's x bar. There's my hypothesized mu of 60. This guy is S, and 18 is N. So we would jam this all in our calculator to get a t-score of 1.712. This is really common. We're gonna have to do this quite a bit, actually, when we're doing hypothesis tests. And then from here, we'll see what we would do with that in just a second. So the way we are going to calculate our, let me just give you a quick example. I'll use this example for how we would calculate a p-value for this number. So t-score of 1.712 means that we would, let's go here. What I would do is I would put that t-score on here. So all t distributions are centered at 0. 1.712 would be, over here somewhere. I'm not concerned with it being to scale or anything. 0.712. And then depending on what kind of hypothesis test we were doing, it's very likely that what we would do is find this area right here. We might actually find this area here as well, depending on what the alternative hypothesis was. Basically, if your alternative hypothesis was just to the right, or it was just a greater than, then we would just find this area. If your alternative hypothesis was not equal to, then we would find both of these areas, which I'll explain when we get to our third example, I think, whatever number 10 is. Coming up, we'll see them in just a bit. Yeah, so that's basically the idea. So this right here would be a p-value, or possibly these two added together if we had a not equal to for our alternative hypothesis. Okay, let's go look at some examples. So we do 3 different hypothesis tests: mu if we know sigma, mu if we don't know sigma, and then p using normal distributions. There's no sigma in qualitative data, right? You can't find the standard deviation of answers that are yes and no. What you can do is you can find the standard deviation of the sampling distribution, which we actually know what that is. It's square root of PQ over n. But that's not a sigma question. Okay. Here's a list of hypothesis testing steps. You can go ahead and read these on your own. I'm just going to do them basically. I'll run you through number 8, and then number 9 and 10 are intended. Again, these are originally notes for my in-person classes. Number 9 and 10, I would have my classes do in class. I'm gonna just go ahead and do them here. I'll sort of write them on the whiteboards, and you can follow along. All right. So here we go. These are the same questions, same hypothesis tests we had like 3 videos ago, by the way. Tire company claims the average lifetime of their tires is 85,000 miles. As a consumer advocate, you are concerned that the tire company's claim is inflated, rip shot, and you know from your previous work with tires that the standard deviation of tire life is 2,500 miles. Take a sample of 48 tires, get an average lifetime of 84,394 miles. So, a couple things to note. Here is the hypothesized mu. Right, that's the mu that's going to go in our hypotheses. We have a sample size of 48 and an X bar of 84,394. We know, essentially by magic here, that sigma is 2,500. So, since we know sigma and we are doing a hypothesis test about mu, we are doing this first one that I had on the list, right? Test of mu if we know sigma using normal distributions. Calculator calls this a z-test. I'll show you how to do that on your calculator in just a second. But I want to show you how to calculate the p-value first. So questions asking about a mean. We have sigma, so we should do a z-test for means. All right. I mentioned all the numbers, right? 85,000 is mu. That's because they're referring to the lifetime of all their tires. That's the mean that they are claiming. 2,500 is sigma because we know that in general tire life has a standard deviation of 2,500 miles. And by the way, I have no idea if that's true. I just made up that number. But for the purposes of this problem, that's what we're assuming tire life standard deviation is. And then n's 48, x bar is 84,394. Okay. Here are our hypotheses. They're the same ones we wrote 2 videos ago. 3 videos ago. I don't know what video number this is. The null hypothesis is that mu is greater than or equal to 85,000, and the alternative is that it's not, it's less than. Okay. We want to find the null distribution, right? The sampling distribution, capital X bar, that is associated with the null hypothesis, which is to say that mu is equal to 85,000, right? If the population mean is actually 85,000, what would the sampling distribution of X bar be? Central limit theorem gives us this, right? That's what the central limit theorem tells us. Right, and so we just quote the central limit theorem here. Capital X bar is normally distributed with a mean of, well, 85,000 is our hypothesized mu, and a standard deviation of sigma, which is 2,500 over the square root of n, which is 48. So we find this, and there we go. So I want to draw this. So I do that here, right? I actually draw that distribution on my computer. And then what I do from there is I put on our actual observation, because remember, everything along the x-axis here is the value of some x bar. Well, our x bar is one of those, right? And here it is, 84,394. Our alternative hypothesis is that mu is less than 85,000. So remember, the way you calculate the p-value, so the p-value is the probability of getting the statistic that we actually got, or one that is even farther in the direction indicated in the alternative hypothesis. That means, in this case, to the left. So the probability, if the null hypothesis is actually true, which is, say, on this distribution, of getting what we actually saw, or in this case, less than that. Well, that's this area, right? That's just normal CDF. So the p-value is this shaded in blue area here. And that is just this, normal CDF minus infinity up to 84,394, with a mean of 85,000 and a standard deviation of this, 360.84. I probably shouldn't say standard deviation. I should say standard error of 360.84, right? Standard deviation should really refer to this 2,500. So we put this into our calculator and we get this number, 0.0465. That number is smaller than our alpha of 5%. Very slightly, right? It's just a little bit small. So in reality, you should probably take a bigger sample. But if this is all we're going to get, then that number that we got, the p-value here, is smaller than 5%. So we should reject the null hypothesis. We reject the null hypothesis. Remember that our hypotheses were that the mean lifetime is at least 85,000 miles, or the mean lifetime is not. It's less than 85,000. Well, we rejected the null hypothesis, so our conclusion is that this is true, that the mean lifetime of these tires is less than 85,000 miles, which is bad for the company. Right? We're essentially saying we have enough evidence to suggest that you are being dishonest with your statement about your tires. In reality, what we should really do is probably do the test again if we have the time and or money for it. Because this is close to 5%. It's near the border, right? We don't necessarily want to go around making accusations willy-nilly. So anyway, we should say something to the effect of this tire company appears to be inflating the claims of their tire lifetime, or the lifetime of this company's tires is not as long as they say it is. Something to that effect. So there you go. According to our test, this company appears to be overstating the lifetime of their tires. Very simple. Okay, so this is kind of your basic example of how to find a p-value. Graph your null distribution. Put your actual observation, or the observation that you got from the data on there. And then shade in the direction indicated by your alternative hypothesis, in this case, less than. So left. And then find that area, find that shaded in area, and that's your p-value. You take that p-value, you compare it to alpha, decide if you're going to reject the null hypothesis or not, write a conclusion, there you go. So as you can see, hypothesis testing has a few steps to it. So this is a thing that you want to practice. You want to be good at this. This is a thing we're going to do a lot of, and in fact, the third midterm is, I don't want to say nothing but hypothesis testing. There's other stuff, but a lot of it a lot of it is hypothesis testing. And in fact, a lot of the second midterm is hypothesis testing as well. Less, but still a lot. So let's do another problem. So this one I will write out as we go. So what type of test should Lauren do? That's the first question we have to ask. So let's read. Past studies have found that giraffes average 15.5 feet tall. Lauren thinks that due to habitat loss, giraffes are getting taller because they have fewer acacia leaves that they can reach, and therefore have to grow taller. Like it'll be an advantage for them to be taller, so they can reach more leaves. And so she thinks that giraffes are probably taller than they used to be. So she takes a sample of 19 adult giraffes, finds an average of 16.1 feet, average height of 16.1 feet, and an average standard deviation of 0.6 feet in her sample. She's hoping to publish her results, so she will use 0.05, of course. So the type of test that Lauren should do is a t-test for means, for a couple of reasons. One, her sample is small, smaller than size 30, and that's what t-tests were originally developed for, or t-statistics were originally developed for. And two, she does not have sigma. She does not have population standard deviation. All she has is, the only standard deviation she's got is her sample standard deviation, so she has to use that. So if I wanted to label all the numbers, this is our mu. That's our proposed mu, the number we're going to be comparing to. 19 is n, that is our sample size. 16.1 is x bar, because that is our sample mean. And 0.6 is s, that's our sample standard deviation. So let's go ahead and write hypotheses. I'm not going to write all those down just for space on the screen, but I will write my hypotheses down. Let's clear all this. So Lauren's hypotheses look something like this. The null hypothesis is that mu, average population average giraffe height, is 15.5 feet, right? Because that's the generally agreed upon number. But Lauren, this is not writing very well. HA. My goodness, that's an A and this is a 0. The alternative hypothesis, Lauren thinks that giraffes are actually taller than 15.5 feet because they have to be with habitat loss. That's her hypothesis. So the greater than means that when we find our null distribution, we are going to be shading to the right. Now, our null distribution is not given directly by the central limit theorem here. We have to calculate a t-score, because remember, we're doing a t-test. So the t-score that we get is going to look something like this. T is x bar minus mu over s over root n. Well, we have all those numbers, so this is, our x bar was 16.1 minus 15.5 divided by 0.6, which was s over the square root of 19. Some people mess up and say 18 there. It's not right. It is 19. It's not degrees of freedom. It is the actual sample size there. So we're going to jam that all into our calculator. Let's go ahead and switch over to that. I believe I still have that up. Don't die. Show all windows. Don't die. Hang on. One second. Calculator, what are you doing to me here? Won't come up. It's frozen. Great. All right, well, I'm going to go ahead and open that up. I'm going to go ahead and pause the recording. I'll open that back up in just a second. Okay, I've got the calculator back open. It had closed on me due to lack of action. So there's our calculator. So we are going to jam in the things that I said, which I have actually forgotten what they were because it's been a couple minutes. All right, 16.1 minus 15.5 divided by 0.6 over root 19. Okay, so when you're doing this in your calculator, be sure to use parentheses. So I'm going to do parentheses, 13. 16.1. I said I was going to use parentheses and I didn't use them. 16.1 minus That's times. Typo-filled video here. 15.5 divided by, here's where the parentheses are really important. 0.6 divided by the square root of 19. And this is my t-score. This problem of 4.359. Maybe 4.36 would be fine. I'll go 4.36. Okay, so let's write that down. About equal to, let me get my picture out of the way here. About equal to 4.36. Okay, so here's what we're going to do. Once we have calculated our t-score, I'm going to draw my distribution, right? You always want to draw your distribution, draw your null distribution. Here's mine. This is t with 18 degrees of freedom because our sample size was 19. Always centered at 0. 4.36 is over here. It's actually farther to the right, but that's fine. I just want a visual aid. And the way I'm going to shade is I'm going to shade in the direction indicated by the alternative hypothesis, which is to the right. Right? U greater than 15.5 corresponds with t greater than 4.36. So that. I'm going to find this area using my calculator, which I don't know if we've done TCDF yet. I think we haven't. Functions pretty much like normal CDF. So here's how you do it. I will show you one right here. So the way you do TCDF in your calculator is pretty much the same as normal CDF. It's just instead of putting in mean and standard deviation, you just put in degrees of freedom. That's it. We had 18 degrees of freedom here. So I'm going to go to second vars TCDF. Okay. We're going to go from 4.36 up to infinity with 18 degrees of freedom. So the lower and upper are exactly the same as they were for normal CDF. It's just that you tell it what the mean and standard deviation are essentially by putting in the degrees of freedom, or I guess don't standard deviation is by putting in the degrees of freedom rather than calculating it, which is actually a pain in the neck. Yeah, there we go. If you didn't get that interstitial screen there, then you just type it in this order. I would guess that probably none of you have calculators that old, but if you do, there you go. This number is quite small, right? 1.887 seems like a big probability, but it is e negative 4, right? This is times 10 to the negative fourth. That means we're going to take this decimal place and move 4 to the left, so we're going to have 3 zeros, right? 1 and then 3 more zeros. So 0.000189 is what we've got. Very, very small probability. So what I have here is my p-value. Which is TCDF of 4.36 up to infinity with 18 degrees of freedom, which is about equal to 0.000189. Right, so very small. It is very unlikely that if giraffe height was actually 15.5 feet, if mean giraffe height was 15.5 feet, that Lauren would have gotten this sample of 19 giraffes with an average height of 16.1 feet. It is, see, what is that, 0.0189%? So very, very small, right? So she's going to want to reject the null hypothesis. Now, notice that this is smaller than any reasonable alpha. Our alpha of 5%, the standard alpha, is clearly smaller than that. We're going to want to reject that. I forgot what order I asked the questions in, but let's go look. All right, find and sketch the null distribution. We did that. What's Lauren's test statistic? That was the t. That's t equals 4.36. Shade in the area, we did that. Find the p-value, we did that. Compare the p-value to alpha, smaller. Should Lauren reject the null hypothesis? She should. And write an appropriate conclusion. So our sample suggests, or Lauren's sample suggests that giraffes are taller than 15.5 feet. This data suggests, the data suggests giraffe, that's a terrible T, whatever. Giraffes are taller than 15.5 feet. On average, I should say. On average. There you go. That's a hypothesis test from beginning to end. And yeah, not much more to say about it than that, I don't think. You'll get lots of practice on these, though. We're going to do lots of hypothesis testing. Okay, let's try one last example and call it a video. Okay, we've got a 30-year-old study of eye color found that 26% of Americans have blue eyes. We're going to check to see if that's still true. So we take a sample and find that 137 of the people in our sample have blue eyes. So let's see if that is enough evidence to suggest that a different number, that not 26% of Americans have blue eyes. So we have to check to see if we can use the CLT for P prime in this case. You can tell if you can use it by whether or not you have at least 5 successes and 5 failures, where success in this case is have blue eyes and failure is don't have blue eyes, right? And we do. We have 137 successes and 300 and something failures, 363 failures. So plenty on both sides, right? So, but you do have to check that. Sometimes you'll get a sample without enough to make it a normal distribution. So our hypotheses, let's go ahead and write those down. That one, I'm going to go ahead and clear this up. The hypotheses are null hypothesis. Well, absent other information, we're going to go ahead and think that 26% of Americans have blue eyes. And the alternative to that is not 26%. Notice I'm not using mu here, I'm using P, because we are asking a question that is qualitative, and we're asking about a proportion. So let's see what we get. Let's see where we're going with this. Find and sketch the null distribution. So the null distribution is a normal distribution, right? The central limit theorem for proportions tells us what the null distribution is going to be. It says that P prime, capital P prime, is approximately normally distributed with a mean of P and a standard deviation of square root of PQ over N. PQ over N, right? That's what central limit theorem for proportions tells us. The P that we've got here is 26%, because remember, we are assuming that our null hypothesis is true. Whenever you're doing a hypothesis test, first thing you assume, null hypothesis is true. Then we, determine whether we agree with that or not later on. But our assumption of P being 0.26, or our assumption is that P is 0.26. So that means, well, I got to calculate this, square root of PQ over N. Let's go ahead and do that. So square root of P, which is 0.26, times Q, which is 1 minus that. I wrote 0.23, that should be a 6. Which is 1 minus that, so this is 26%, then 100% minus that is 74%, divided by the square root of our sample size, which our sample size was what, 300? Was it 400? 500. 500. So there we go. The standard deviation of our sampling distribution is 0.0196. And you want to go several decimal places here. Even a very small change in the standard deviation can change your conclusion quite a bit, actually. It can change your p-value quite a lot. So I'm going to go 4 decimal places. I feel like that's pretty safe here. 0.0196. So So that would be the same as n 0.26, 0.0196. There we go. Okay, so from here, we're going to draw our distribution, shade it, find our p-value, see what our conclusion is. So this is 0.26, so 26%. And then our standard deviation doesn't go on here anywhere. What we want to do, though, is we want to find out what our actual sample proportion was. Because remember, everything on this x-axis here is a particular p prime, right? So the most common one is 26% if the population proportion is actually 26%. So we take our particular p prime and put it on here. So we had 137 out of 500. So we can go to the calculator and do 137 out of 500 to find our actual p prime, 0.274. And we're going to take that and put it on our distribution. Here's where this gets a little bit different. Our alternative hypothesis is not equal to. It does not tell us to shade to the right or to the left. Here's what we want to think about. We go back to the definition of a p-value real quick. Okay, it's the probability that we would get such a statistic, or one that's even more unusual, if the null hypothesis is true. Even more unusual in this case means farther away from the mean, because this is equally unusual as this, the same thing on the other side, right? Those two things are equally unusual, just in opposite directions. And so more unusual means over here for sure, right? Farther away from the mean than we actually saw, but it also means over here. Because all the p primes over there are also more unusual than 0.274. They're just more unusual in a different direction. So what we want to do is find both of these areas and add them together for our p-value. Now, I don't really have to find them separately because they're the same, right? This area here and this area here are the same area, or have the same value, because normal distributions are symmetric, and t distributions are as well. So if this was a t distribution, you would do the same thing. So what I'm really going to do is I'm actually going to find this area and multiply it by 2, because there's 2 of them. So let's do that. I'm going to do normal CDF of 0.274 up to infinity with a mean of 0.26 and a standard deviation of 0.0196. So we're going to go to second distribution. Normal CDF. What we say 0.274. Upper of infinity, just a lot. Mean is 0.26 and the standard deviation is 0.0196. So that is the area of the upper tail. That's so 0.2375 is the area of this, but I want both of them. So I'm going to multiply that by 2. I just take that number and multiply by 2. So there's our p-value, 0.475. There you go. P-value. About equal to 0.475. Notice that number is big. That's 47.5%. Did we get an alpha in this problem? No, I very cleverly did not give us one. So did we find this? What is P prime? We found that, 0.274, put it on our sketch. We did that. Chain the area, did that. Find the p-value, we did that. Compare the p-value to alpha. So alpha is not given, therefore we should use 5%. Whenever alpha is not given, default, just use the default, right? In the same way that when we were making confidence intervals, if the confidence level was not given, make a 95% confidence interval. If alpha is not given, use 5%. 47.5% is much larger than 5%. We should not reject the null hypothesis. So write an appropriate conclusion. Okay, there is not enough evidence to suggest that the proportion of Americans with blue eyes is different from 26%. That's a lot of words. Let's make a new one here. There is not enough evidence to suggest that the proportion of Americans with blue eyes isn't 26%. Something like that. Something like that. Basically anything that gets that idea across. Okay, was that the last part? I think there's actually one more part to that. One more part to this question. Yeah, make a 95% confidence interval for the proportion of Americans who have blue eyes. So I'm just going to jam that into one prop z interval in the calculator, because there's a point I want to make here. So go to one prop z interval. That is second distributions. No, it's not. That's not right. Sorry, stat tests. One prop z interval. Oh, so just wait, where is it? Oh, z interval. Right. No. One prop z int. Man, sorry, it's getting a little late. I'm getting kind of tired. One prop z int. X was 137 and was 137 and was 500. Confidence level 95%. Let's calculate. So there's the interval. Here's the point I wanted to make. Okay. Let me flip back here so I can show you what question we're answering. Does this interval contain P? It definitely contains P prime, right? Because that's how we made the interval in the first place. Is P prime is right in the middle, so the calculator calls it P hat, like the rest of the world. Your book calls it P prime. So the question is, does this interval contain 26%? And it does, right? Between 23.49 and 31.3 is 26 is definitely in there. So here's the thing about hypothesis tests. Hypothesis tests and confidence intervals do much the same thing if you use them carefully. So I made a 95% confidence interval to go with my 5% alpha. So the idea is this. Let me make it up. What we're doing is basically this. Here was our 26%. When we make a confidence interval, what we do is we start with our, in this case, sample proportion, and then we wrap an interval around it. And the interval that we made here went from 23 up to 31. And so the way you can, or one way to think of a confidence interval is it is what we think of as a range of reasonable values for, in this case, P, the population proportion. And so if 26% is one of those reasonable values, that's going to make us not want to reject the null hypothesis. So it turns out you can do all of your hypothesis testing with confidence intervals if you want to, if you're careful. One thing I didn't do here was show you how to make a one-sided confidence interval, which goes with a one-sided hypothesis test, right? One that's just to the right or to the left. I specifically did this confidence interval with a two-sided alternative hypothesis with a not equal to. Because you have to change the process somewhat if you want to do a one-sided one. I'm not even going to worry about that. The point I wanted to make here is that hypothesis tests and confidence intervals kind of do a lot of the same things, right? They give you a range of reasonable values, or what a confidence interval does is give you a range of reasonable values, and a hypothesis test asks basically, is this number a reasonable value for your parameter? So yeah, they do a lot of similar stuff, and if you're interested in exploring this, I have some extra credit questions that you can answer about that. I'm planning on doing that a little bit later in the semester, but if you're interested in getting into that now, let me know, and I will be happy to set you up with some questions. Yeah, but for now, just notice that 26% our hypothesized mu, or our hypothesized p, being in our confidence interval for p, corresponded with not rejecting the null hypothesis. If it had been outside, like for instance, let's say our interval had been, here, and 26% had not been in our range of reasonable values, then we would have ended up rejecting the null hypothesis. It always works that way. It always works that way, pretty much always. You can come up with some really very finely defined questions where you can get them to differ very slightly, but if you just think of it as always working that way, that's basically true. Okay. So that was the end of our hypothesis test. Make sure you practice this stuff. Have lots of opportunities to practice these as we go along, and we're going to do a lot of hypothesis tests as we go along. And these ones that I'm showing you are actually the kind of simple ones. The later ones aren't really much harder, to be honest. Like, it's just how you calculate the test statistic that gets harder. But the same basic idea applies of, well, where'd my logic go? This, right? Write your hypotheses, gather your sample. This will be find your p-value and compare it to alpha. If your p-value is small, you reject the null hypothesis. If it's not that small, then you don't reject the null hypothesis. That's it. That's how they all go. So, yeah, I think I'm going to go ahead and end the video there. And I will make another one on, stop sharing this. I'll go ahead and make another one about why you compare the p-value to alpha. And then that'll be it for this chapter. So yeah, I will go ahead and do that, and I will see you in the next one.